Hello, everybody. I'm Dr. Shafiq, and I'm your instructor for your geotechnical engineering class. And I would like to welcome all of you in this video session. Okay, today we'll be talking about the grain size of soil. Sometimes we also call that one particle size distribution. Okay, now let me share my screen with you. So you can see the relative soil particle sizes here. So this is clay, actually invisible at this scale. You cannot see that one in your naked eye. This is your silt, this is sand, and this is gravel. Okay, now let's move forward. You can see the size of particles that make up soil vary over a very wide range. So based on that particle size, soil are divided into 4 classes like gravel, sand, silt, and clay. So these relative size of each of these type of particles are shown here, as I told you right now. You can also see here that sometimes we also classify the sand as fine sand, medium sand, and coarse sand. So this is your sand. So it could be fine sand, medium sand, and coarse sand. So here you can see your clay is basically just like a small, point down there. This is your silt, this is fine sand, this is medium sand, and this is coarse sand. Okay. Now there are several methods how you can classify your particle size. So the first two is MIT method and USDA method. We usually don't use that one for geotechnical purpose. So I'm not going to include that one in our discussion. But you can see here the American Association of State Highway and Transportation Officials, which is called the ASTO, and also Unified Soil Classification System, which is also called the USCS method. These two methods are widely used for geotechnical engineering. So ASTO method is basically related with transport, highway and transportation, like roadway construction cases. On the other hand, USCS method is used for like building bridges and other kind of structures. Okay. Now, if I see the scale here, then basically you can see that this is your ASTO method. So anything smaller than 0.002 millimeter, that's actually your clay. From 0.002 to 0.075, that's basically your silt. From 0.075 to 2 millimeter, that's your sand. And 2 to 76 millimeter, that's basically your gravel. On the other hand, for USCS classification system, you can see some similarities with ASTO that anything smaller than 0.075, they call that one fines. Okay, anything smaller than 0.075 millimeter in ASTO method, they call that one silt and clay. And USCS method, they call that one fines. So 0.075 is kind of a very important milestone. Anything smaller than that is basically fines, or we call that one silt and clay according to ASTO method. And again, from 0.075 millimeter to 4.7 millimeter, that's basically your sand for USCS method. And anything bigger than 4.75 millimeter to 76 millimeter, that's your gravel. Now you can see how we can find out the particle size of a mass of soil. So what we do, we usually sieve that one. Okay. So what we usually do, we take not just one sieve at a time and do the analysis to see that how much is passing and how much is retaining in each of the sieve. That would be very time consuming. So what we usually do, we take like the bottom is just a pan, doesn't have any opening. Then you have the number 200 at the lowest, or smallest mesh size. And then the second one would be second smallest, then the third smallest, the fourth smallest, and at the top you will have the highest, um, opening size. Then we can take a bunch of them, maybe like 8 or 10 together. And at the top one, we will just put like some known amount of soil there, okay? Usually very dry soil so that the lumps are broken into just particles. Then we keep that one in a shaker and shake that one for 15-20 minutes in a standard shaker. And at the end of the shaking, like we just take each of the sieve and measure that how much is retained in each of the sieves. Okay, that's the way we try to see that how much is passing each of the sieves. Now let's see some standard sieve size here. You can see the biggest one is number 4, which is opening has 4.75 millimeter, almost like a couple of inches here. No, sorry, uh, 4.75 millimeter, that's actually 0.47 centimeter, right? Yeah. And then you can see the smallest one is here, they're saying 270, but actually the smallest I can see in the market is actually 0.075, even though they say like 270, but it's very difficult to make this, like the mesh size so small. Uh, so actually, even though it's in the text in the literature, but when I wanted to buy for the, like lab, we couldn't get that one in the market. Okay, so the smallest or finest mesh is actually number 200, which has an opening of 0.075. You know that 0.075 is a milestone. I said earlier that anything smaller than 0.075, according to ASTO, we call that one silt and clay. According to USCS, we call that one fines. Okay. Now, this one is actually once we do our uh, sieve analysis, and after some calculation, we can just draw a curve like this, which is basically percent passing. Sometimes we call that 1% finer. And this is the particle size in log scale. And this one looks like a invert S-shaped curve. And we call that one particle size distribution curve. Sometimes it's also called that one grain size distribution curve. Okay. This one actually very, very important and tell you a lot of things um, about the soil. Now, let's say this is one of that particle size distribution curve, and according to ASTO method, you can see anything 0.075 smaller than that. That's basically your um, silt and clay, and anything bigger than 2 millimeter is actually your gravel. So if you draw that line here and draw that line here, then you can see this is basically your uh, silt and clay. That's basically 16% here. If you read that scale, it's 16 here. If you read that one here, then basically it's 19% gravel, and the rest is actually your sand. So what is that rest? That's total 100 minus 19 minus 16. That's basically 100 minus 19 minus 16. That's 65% sand. So you can see from that curve, actually you can tell from the ASTO method that you have 16% fines, 65% sand, and 19% gravel. Okay. Now, if you want to do that one in ASTO method, you can remember that 0.075 is the milestone, but anything bigger than 4.75 or anything that retains in number 4 seed, that's basically your um, gravel here. So I have to move that line from here to 4.75. Now let's see that one in the next figure here. So you can see this is your 0.075 line, and this is 4.75 now. So if I draw the line here and here, now anything above that line is actually your gravel. So you can see actually your fines remain same, which is 16%, but now your gravel is very smaller percentage, which is like 3% gravel, and the rest is your sand. So how much is that rest? That's actually 100 minus 3 minus 16. So that's 81% sand. So according to USCS method, you can say that soil has 16% fine, which is same as your ASTO method. But now you have different amount of sand and gravel here. So here, according to USCS method, you have 81% sand and 3% gravel. Okay. Now let's move forward. That in the sieve analysis, you can see the smallest mesh you can get is 200, which has an opening of 0.075. So anything smaller than 0.075 or that passes number 200 sieve is your silt and clay. But how do you know the distribution of that silt and clay? Distribution of size of that silt and clay, because you don't have any sieve smaller than that. So can you do that? Yes, we can do that. Actually, we use the hydrometer test to find out the grain size or particle size distribution of the particles which is smaller than 0.075 or passes number 200 sieves. But this hydrometer test is not in the syllabus, so I'm not gonna discuss about that. But I only want to convey that message to you that actually you can do that, okay? Now you can see here in this figure that this is your number 200 sieve. So anything, this is the last point you get from the sieve analysis, like all that, like circle here, solid circles are here. Anything is smaller than 200 sieve, actually, you take that passing like 200 soil and then use the hydrometer test and you can find out the distribution of that one here, okay? So if you can add together, then basically you can see you have a particle size from all the way from here to here. Okay. Now, if I draw the line here to see that how much is my silt and clay, how much is my sand, and how much is the gravel according to Unified Classification System or USCS system, then what I have to do, I have to draw a line here first at 0.075 or 200 sieve. Okay, so anything that passes here, that's actually your fines. And then you have to draw another line at 4.75. And you can see actually this is your number 200. So anything that passing this 200 actually is your fines. How much is that? That's actually 60% here, right? 60% fines. And you can also see that number 4 sieve is here, actually nothing retained on number 4. Everything passed through number 4. Means like what? Since the retain is 0, so basically you don't have any gravel there. So rest of the amount has to be your sand. So that rest amount is actually 40%. That's actually your sand. Okay. Now let's move forward, and you can see that you can also find out some carved parameters from this particle size distribution curve, which is very, very important for soil classification and to understand the nature of the distribution of the particle size. Now, first of all, it's called the effective grain size, which is D10, means the diameter of the particle corresponds to 10% finer. Okay, so if you draw a line for 10% finer here and the corresponding diameter, read that one from that scale, that's actually your D10. Similarly, you can find out it uniformity coefficient, which is CEU, actually D60 by D10. So what is D60? D60 is the diameter of the particle corresponds to 60% passing. So actually here, 60% passing. So if you draw a line here, come here, read that one from here, that's actually your D60. Okay. You can also find out your D30 from the 30 line here, or D25, D35, or 65. That depends on you, like what is that value there. You can just read that one from that chart. But the most important part is your D60, D10, and D30, because you need D60, D30, and D10 for your CEU, for the calculation of your CEU and your CC, because these two parameters are extremely important to classify the soil. Okay, which we'll discuss in chapter 5 or 6. Okay, so now let's see here that how you can just use that parameters for this particular case here. Okay, so let's say I'm first trying to find out my D10. So I have to come here, find out, draw a line from 10 line here, and that intersects with this particle size distribution curve at here. And if I go here and try to read that one from that scale, so this one is actually 0.0015. So my D10 is 0.0015 millimeter. Okay. Now I just try to do that one for 30. So draw a line here and try to read that one from here, which is 0.015. So my D30 is 0.015. Now go to 60 and then try to see that one here. Read this one from this scale, which is actually 0.07. So my D60 is 0.07 millimeter. Now I can easily calculate my D10 or effective grain size, which is actually your D10, which is basically 0.0015 millimeter. What about your CU? CU is nothing but D60 by D10. So if you just plug that value here, you get 47. Now what that number means, you'll see that one when you classify the soil. If this number is higher, this means like your soil has a very wide range. So different size of particles are there. If your CU is small, then basically you will see that your CU value is very low. Actually, your CU value could be as low as 1 if all the particles are same size, like glass marble ball, like same size, then basically you will see that the distribution curve would like a vertical line, and your D60 and D10 would be same value, and you will get your CU equal to 1. So higher the value of CU means like you have a wide range particles in your soil. Now let's try to find our CC, which is basically D30 squared divided by D60 by D10. If you just plug that value, then basically this one is 2.14. your CC value from 1 to 3, in between 1 to 3 is actually good. Anything less than 1 or higher than 3 is not good. Means like it's not well uh, distributed. Well, now you can just take a look here that from that curve, actually, we can tell that whether the soil is well graded, poorly graded, or gap graded. So well graded soil means like that invert S-shaped curve has a long range from here to here. Range is very high from here to here. On the other hand, the poorly soil, you can see the range is from only from here to here. So if you compare this one and this one, then basically this one has well-graded means like the range is wider, means better. And then if the range is not that high, then basically it's poorly graded. And if you have like something like that, and then there is a gap here, and then something like this, then basically this one is gap graded, means like they have like uniform size, and then they don't have like any particle from a particular size from here to here, and then you have, you know, like particle size uniformly distributed above that. So this is all called the gap graded soil. Okay, so poorly graded soil and gap graded soil is not good in terms of geotechnical engineering. On the other hand, well graded soil is always better. Now let's take a look of an example problem. Okay, so this one is saying that this is the result of a sieve analysis. Draw the particle size distribution curve and find out the following things: a percent of sand according to ASTO method and coefficient of gradation of the soil. Okay, so you can see here, this is your sieve number, and this is how much soil retained in each of the sieves. Okay, each of the sieve. So what you can see here, that they gave you a standard sieve number, but they didn't give you the opening of that sieve. So that's why we have to find out the list of that US standard sieve size. So if you see here, this is your sieve number. From there, you can just read what would be your opening here. So you can see here, we have 1, 2, 3, 4, 5, 6, 7, 8 sieves and a pan. So this is my sieve 1, 2, 3, 4, 5, 6, 7, 8 sieves here. And the corresponding opening is given here. Okay. You need that opening to draw your particle size distribution curve. So that's actually given here, this one and this one, column 1 and 3 given from the sieve analysis. Column 2, you got that one from the US standard sieve size. Okay. Now this one is important here, that how we fill this column here. This one is saying that cumulative mass retained. Just try to assume that one, rather than taking all those things, if you just take one of that sieve and fill that one with the total amount of soil, which is 729 gram. I just added all of them together, okay? 729 gram. Now let's say if I take that 729 gram soil in that sieve, how much will be retained there? You can see that anything, like if you add this, how much retain on that sieve, and anything that retain above that sieves will retain in number 60, right? Because they are bigger particles. So they will definitely retain on number 60. So that's actually called the cumulative mass retained. So I wrote that one here, that add the retained amount of sieve with retained in all sieve above that particular sieve. Okay. So if you say like 80, then basically this one has to be 122 plus all of them. together, plus these, plus this, plus this, plus this, plus this. But when I'm calculating that one, then I'm just calculating this equal to 0, then this one 40 plus 0, that's 40, then 60 plus 40, that's 100, then 100 plus 89, that 189, then 140 plus 189, that's actually 329. That's the way, all the way when I come that one, it has to be 729, which is equal to the total mass of the soil. What does it mean? This means like if you keep like 729 gram of soil in a pan which doesn't have any opening and shake that one, then basically you are gonna get 729 gram retain on the pan, right? So this one has to match with that. Now, the percent cumulative mass. So I'm just gonna express this one in terms of percentage of the total, okay? So that's actually 40 divided by 729 into 100. That's actually 5.5. Then 100 divided by 729 into 100, that's actually 13.7. That's all the way you have to calculate that one here. And finally, in the pan, it must have to be 100%. Okay. Now the percent finer. If you take any particular sieve, let's say 30% retained. So how much is passing? That 100% minus 30%, 70%, right? So you subtract that cumulative written, like in terms of percentage from 100 to get your percent finer. So that's basically what we are doing here. So column 6 equal to 100 minus column 5. So this one is actually 100 minus 0, that's 100, 100 minus 5.5, that's 94.5, and so on. So you can do that one very easily using your Excel sheet. Okay, once you get that one, then basically your particle size distribution curve is nothing but that percent finer versus your opening size, like of your sieve curve. So if you draw that one here, you see this is your particle size distribution curve. Try to remember always that this is a log scale and this is normal scale here. Okay, and this one starts like reverse order, like this is 10, 1, 0.1, 0.01, and so on. Okay. Now, first of all, I have to find out once we get that particle size distribution curve, the problem is asking to find out how much is sand according to ASTO. Okay. To find that out, you know that I have to find out like 0.075, that how much is passing to 0.05. So I'll draw that curve here, this one, like intersect with that line here. So if I try to see that amount here, and then I also try to see according to ASTO method that anything that retains number 10, sieve, which has an opening of 2 millimeter, that's basically our gravel. So it intersect here, so I'll draw a line from here. So anything that retains, anything that passes like 0.075, sieve, that actually your silt and clay, which is basically 1.7%. And if you see that how much is your gravel, that's basically from here to here, that's actually 5.5% gravel. So how much is your sand? That's from here to here. So that has to be 100 minus 5.5 minus 1.7. So 92.8% sand according to ASTO method. Okay. Now let's try to see the second part B of that problem. So we have to find out our CC for this soil, coefficient of gradation. So which is equal to D30 squared divided by D60 by D10. So I need to find out my D10, D30, and D60. So how can I find out my D10? Just go to 10 here. This is 0, 20, so that's in the middle here. And then draw a line here. Read this one, that how much is that? That's actually 0.15. So basically my D10 is 0.15 millimeter. Now let's say for 30, you draw a line here that intersect here. So you just draw another line here, try to read it from that scale, which is 0.17. So my D30 is 0.17 millimeter. Now do that one for D60. So this is your 60, draw a line here and try to read the corresponding diameter of the particle from this scale. And you can see this one is 0.27 here. Okay, there is a mistake here, 0.27. So my D6 is 0.27 millimeter. Okay, so now I can calculate my CC, which is basically D30 squared divided by D60 by D10. If I plug all that value from here, then basically I get a value of 0.71. As I said earlier, that your CC value in between 1 and 3 is good. Anything less than 1 and greater than 3 is not that good. So basically that distribution is not that good. You can see this one is like going to a straight here and then going like that. The good one will be like this. Okay, just go like this. Anyway, so that's the answer for this particular problem. Now, we also need to know the shape of the particle because this is also very important for the physical property of soil, means like the strength property of soil. So particle shape is very difficult to define and measure because they are very small in size, right? But based on the size, we can just divide the particles into three different shapes, like bulky shape, flaky shape, and needle shape. From the name, you can understand that this one is kind of bulky. This one is like flaky, like sheet type, like mica sheet. And the needle type is basically like needle, like attapulgite clay minerals are kind of needle shaped. Okay. Now you can also see that the bulky shape, we can also have like four subdivision of that, like angular, subangular, subrounded, and rounded particles. So this is your angular particles, this is subangular here, this is subrounded, and this is rounded. So it's very difficult to actually figure out which one is angular, which one is subangular or subrounded. So usually we try to do that one like electronic microscope, or sometimes just in normal microscope. Take like for sand particles or silt particles, like 10 to 20 different, like grains, and try to see that one in the microscope, that how many of them are angular and how many of them are um, rounded, and then try to find out the percentage from there for the overall distribution of the particle size, for particle shape. Okay, that's the way you usually do that one. Anyway, so that's basically um, all about our grain size distribution of soil. So if you have any question, just don't hesitate to contact me, either email or just come to the office hours, and we can discuss everything in the Zoom session. Okay, so thank you for your attention.